Hi everyone. So today we'll be discussing how to program a PIC microcontroller using C programming language. In particular, we'll be looking at the PIC 16F877A, which is fairly common here. It has 40 pins, as you can see, although it has other packages. But for this one, we will focus on the 40-pin PDIP package. And again, it has 40 pins. Okay, and for now, what I want you to focus on is the names of the pins. So these pins are actually grouped into ports. And for the 877A, the ports are from A to E. So you have port A pins, port B pins, port C pins, D pins, and you have port E pins. Then of course you have your supply, you have your positive source, and you have your negative source. So you have your VDD and VSS, and actually these are on both sides. So you have your VDD VSS here, then you have another VDD VSS here. So VDD is your positive source, VSS is your negative source, or which is commonly connected to ground. Okay, so we'll be using this device. Later on, we will be coding using XC8. Okay, that's the C programming language used by Microchip. And then, we, of course, we'll be using MPLAB X. And then we will be simulating using ISIS, Proteus ISIS. Okay, so let's start with MPLAB X. So let me open my MPLAB. Okay, so I have here version 5.3. This is the version where you can still code in assembly. The version 5.4, I think that's the newest version. Microchip disabled assembly language programming completely. So this is the version where you can still code in assembly, but then again, we'll be coding in C in this video, so doesn't matter really. So you can use version 5.3 or version 5.4. You can still follow our tutorial here. So let me just delete this old code here so that we can start fresh. Okay, so the first thing you need to do is to create a new project. So you'll go to File and New Project. And here, just select Standalone Project and click Next. And here you select your microcontroller, your device. So as I presented earlier, we'll be using the PIC 16F877. Okay, click Next. Okay, so for your tool, just click Next. Then for the compiler, again, we will be using C or XC8. So select XC8. By the way, XC8 and the MPLAB are both separate executables. You can download the MPLAB X installer for free. You can also download the XC8 installer for free on the Microchip website. So usually you install MPLAB X first, then after that you install XC8. Then your XC8 compiler will appear here. So I'll be just giving you the links for the installers, maybe on the description of this video. And okay, going back, you select XC8 here, select Next, then give your project a name. So we start with a very basic C project. Try to flash or blink an LED connected to one of the ports of your microcontroller. So just name this blink _ C or say XC, since I already have a project name C. Alright, then of course don't forget to check this checkbox so that when you click compile, this project will be the one compiled. Okay, so click finish. So here in the left panel, you have your project explorer. So what you want to do is just right click on source files, then new, then select main.c to create a new blank C file. Just select that, then give it name. So usually you can just write main.c. Okay, so let's say main.c or main. No need to write the extension because it will automatically add the extension. And you see here below, this is the location of that file that you will be creating. And you just click on finish. Alright, so you have a template, very basic template for your C file. And the requirement for every C file is that it should have a main function. And if your project have multiple C files, then it should only have one main function, because that is the first thing that your compiler will look at, your main function. Similar to how it goes in C or C++ programming and other platforms. So this is your basic template. And again, what we'll be doing is write a code which blinks one port or pin in your PIC microcontroller. Now going back to our pinout right here, let's just select one pin from this set of pins, this 40 pins. So let's say I will be selecting, this one, RB0, alright, RB0. So if you want to make this pin an output, or by connecting an LED in this pin, first thing you need to do is manipulate the corresponding trace register. So for every port, there is a corresponding trace register. So as you can see, there are ports, multiple ports, right? You have your port A, port B, up to port E. That also corresponds to having trace ports. So you also have your trace A, trace B, trace C, trace D, and trace E. Okay? And to make things simple, in making a pin as an output pin, for example, you want to make RB0 an output pin, you must make its corresponding trace pin low. Conversely, if you want to make the pin RB0 as an input pin, then you must make its corresponding trace B0 pin high. So basically, that's how you create or initialize a pin as either an input or output. So in code, that would be trace B0 equals 0. Of course, don't forget the semicolon. So this is making RB0 as output. Okay. Again, if you make this equal to 1 or high, then that would make RB0 as an input pin. So basically that's it. Then you want to make the flashing continuous. Alright, so we want it to be on an infinite loop. Okay, so we'll be using an infinite while loop. Okay, so one technique I use is just write while 1 like that. And then you have your parentheses, of course, or curly brackets, I'm sorry. So whatever is inside these brackets would be executed continuously or infinitely, at least while your microcontroller is turned on. So here we'll be writing the code for turning on the pin. So that is just RB0 equals to 1. Okay. And then to turn it off, we write RB0 equals to 0. But of course, if you make it like this one, you will not be able to see the blinking because this would be executed so fast. Okay, so each line will be executed very fast that you cannot see it, or our eyes can't catch when the LED turned on or when it turned off. So basically, depending on your crystal frequency, every line would be executed at a rate of 4 divided by your crystal frequency. Okay, so you should introduce a delay in between turning on the LED and turning off the LED. So here in XC8, you can just use the delay function. So that's 2 underscores. Then you have your delay underscore ms. So that's in milliseconds. So for example, if you want a delay of 1 second, just write at 1000. And then just copy this one for the delay after turning off the LED. Now, this delay won't work if you won't specify your crystal frequency. So in XC8, specifying your crystal frequency is in code. So you can just use a define, and that define is like this. And that would be underscore crystal or xtal, and underscore frequency of then this constant would be equal to your desired crystal frequency. So we usually use a 4 megahertz crystal. Okay, 4 megahertz crystal. The reason for this one is that since the formula for your instruction cycle, just write it here. The formula for instruction cycle is 4 divided by the crystal frequency in megahertz, right? This is in the data sheet of the for every microcontroller. Okay, so this is the formula. Then each line would be executed at this speed, depending on what type of, by the way, what type of command is used. So there are other those that goes or branches out from one point to another would have different instruction cycle, and so on. But typically, if you have a line like this one, this would be executed at around the instruction cycle. Okay. So the reason we're using 4 megahertz is that it's easy to visualize the instruction cycle speed, right? So for example, if you have 4 million hertz or 4 megahertz in the denominator here, then that would be 4 divided by 4 million, and you have an instruction cycle of 1 microsecond. So that would be easier for us to visualize that each line is executed at 1 microsecond. Okay, but of course you can use other crystal frequencies. Just make sure that whatever is on your circuit is the same as in your declaration here. Okay, so that is okay. So this is it. We use a 4 megahertz crystal, and then we can now use the delay. So basically, this is your blink code. Alright, this is your blink code, and then you can go to production, build main project, or just press F11. Okay, so build main project or press F11. Then wait for the build successful string or text to appear. So that's it. So it's in here that our build or our code contains no error. So we have now our hex file. Okay, so this is the one we need that should be loaded to your microcontroller. So for now, we'll be just simulating our microcontroller project. Will not later, or maybe later, I will show you how to actually load the program using a applicable programmer, both the device and a software. For now, let's copy this hex location. Okay, then we will open our approaches program. Okay, so this is actually the approaches 8. Okay, so for the simulation, circuit simulation, we'll click on ISIS. Alright, then once we have our workspace, we click on the component mode. Okay, component mode, then we click the P or the PIC device. Then we just type in our microcontroller of choice, that is PIC or PIC 6087788. Okay, so just click that. Okay, then click on the workspace. Alright, so this is our 40-pin PIC 6087788. Now, specify the program for this one. You just double click. You have your fields here. So you have your program file field. You just paste the one you copied from MPLAB earlier. Alright. Then don't forget to change your processor clock frequency. So whatever your declaration in code should match here. So since we used 4 megahertz there in our code, we'll be using also 4 megahertz here. Just click OK. And this would actually work now, although we don't have any external crystal frequency here. Alright. In reality, we actually need to wire the crystal here since we are using an external crystal. But more on that later on. So we'll disconnect an LED on RB0. So again, we go to PIC device and LED. So we will use the animated model. Okay, this one. Alright, so it's actually good design practice to add a resistor in series with your LED, although nothing will happen here because you don't add a resistor. It would be good practice if you can just add a resistor in series so that the current across your LED would not be too much that it would burn your LED. So let's just use 120 ohm resistor. Okay. By the way, the pin could produce around 25 milliamps of current. So if you would use no resistor in an actual circuit, of course, then with prolonged use, your LED might burn out. So it's really advisable to use a resistor in series. Okay, so just connect it like this one, then of course you add ground. Okay, and you play. So your, oops, sorry about that. There's a missing connection somewhere. Just rewire it. This is the animated. Actually, you can see that it's already blinking. Red is high state, blue is rest. Maybe I've used the wrong model. So let me just check. Yeah, I think so. So maybe my resistor value is too high. So let's reduce this to 100 ohms. Nope. So let me just remove this one. Okay. That's weird. Oh man, I know. I think the reason. Maybe on this side right here. So there was a misconnection between the cathode and the ground. That's why it didn't turn on the first time. Let me just bring back the resistor again for good design practice, especially for our young engineers out there. So it is good, right? That's good. That's a good value. Alright, so it's now turned on and it's blinking. So that's about it. Okay. Now, if of course we want to change our pin, obviously we need to change our code, both the trace and the port. Okay, so for example, I want to change, I will reconnect this LED to this pin, RC0. So I need to modify my code here. So I will be changing this to C, and also this one to C. Okay. So if that's the case, we need to rebuild. Okay, that's successful. So don't need to reload the code here. Just stop, and then you play again. And this time, RC0 is the one blinking, not RB0. So you just need to transfer the wire here, and that should make the LED blink. Alright. Now how about if you want to make a pin as an input? Okay, in C, again in C. So by that, let me just create a new project. So, file, new project, then just click standalone, then next, select your device, next, then it's 8, next, then this one, I will name it input. Right, so we'll be using input switch in particular, so click finish. Alright, so notice that input now is in boldface because it's now our main project. So every time you click production and build main project, this is the project that will be compiled. If you want to go back to Blink, just go to Blink, right click, and then select set as main project. For now, we'll be using input as our new main project. So same way, you right click on source files, and new, then main.c. Okay, similarly, we'll give this name main. Then you can just copy this part right here and be using the same crystal value. And then we'll be using a pin as an input, then its corresponding trace pin should be high or equal to 1. So going back again to our pin out, let's say that we want this pin right here as an input. Pin 33 again, that would be RB0. We want to make this as an input, so we just write in our code, just be 0 equals to 1. And that would make RB0 as an input. Okay, then again we use an infinite loop to make our program continuous. So here we'll be using an if statement to check the state of our pin. So that would be just if, okay, then RB0, because so it can either be a 1 or a 0, but that would be depending on how you would wire your switch. So going back to our circuit, okay, so this is my circuit right here. Now if I will make this pin as an input, so we will be wiring a switch here. So again, we will be going to pick devices, switch. Okay, so use this one, interactive PST switch, latch action. Okay, so that would be this one. There are two ways to wire the switch. One is what we call a normally high switch, or active high, or yeah, and we have a normally high switch or active low. Okay, so let me show you the difference between these two after I rearrange this one, okay, to make our circuit not messy. Okay, so this is our switch. What we need is a resistor. Okay, so typically the resistor has a value of 10K, because that would be enough to limit the current towards the pin. Okay, then place your, so for example, you want a active low switch, just place the power source the other end of your resistor, and on the other end of your switch you place your ground. So this is an active low switch, or a normally high switch. What happens here is, if you press the switch, your pin will be connected to ground. Okay, and if this is open, your pin will be high, since it will be going towards your positive source. Now the resistor is here so that when the switch is turned on, your positive source and your ground will not be shorted out, which would be trouble for your circuit. So this resistor is actually important, right? So we call this a pull-up resistor, and actually you can the device actually has an or multiple internal resistors, but that's for a later discussion. For now, you should know that when you see a switch, a button, then you should use a pull-up resistor like this one. So this is a normally high switch or an active low switch. If you want the other way around, you can just replace, or you can just interchange the power, the positive source, and the ground. So if you can just delete this one, you place ground on the end of the resistor, then you place power, your positive source, on the end of the switch, and this becomes a normally low switch or an active high switch. Alright, so if you look at it carefully, when this switch is open, your pin will be connected to ground. So when this is open, your pin is low. When you turn on the switch, your pin will be connected to your positive source. That would make your pin high. Okay, so let's say we will select this switch arrangement. So we'll be using the normally low switch, right? So here, if we turn on the switch, your pin will be high. If we turn off the switch, our pin will be low. Okay, so in our code, okay, in our if statement, okay, we'll start with if RB0 is 1, and that is when your switch is turned on, right? And that's the case. Let's make the LED on RC0 turned on whenever your switch is on. So we will add another trace here. That would be trace 0 equals to 0, since we are attaching an output device on RC0. So that would make RC0 as an output pin. Okay. Here on our if statement, if the switch is on, that is when RB0 equals to 1, then RC0 should be on. Otherwise, we only have two possible values here for RB0, 1 or 0, right? So just write else, then you turn off RC0. So again, when the switch is on, is when RB0 is 1, then you turn on LED. Else, that is when the switch is off and your RB0 is low, then you turn off the LED. Okay, so build this project. Again, we copy the X file. Go back to Proteus. This time we need to reload the code because this is different code. So again, double click, then just highlight this one, then paste or Control V. Change the code. Click OK. Click play, and let's see what happens. So this is turned off, right? And your LED is turned off. So I click the switch, your LED turns on. And if I turn off the switch, my LED turns off. So this is just the basic sample of controlling an output device. In this example, an LED using a switch as an input.